Good morning. So today's lesson will be covering sound and sound design. So to begin, nothing you see or hear in theater is arbitrary. Everything is planned. The actors are selected because the director believes they have that magical something that will allow them to become the characters. The color, textures, and shape of the set, costumes, props, and lighting are all designed to help the audience sort of quote unquote enter the world of the play. The rhythms and timing of the scene shifts and lighting changes are all carefully planned and rehearsed to keep the audience's attention on the play. Everything is planned, designed, and created to draw the audience into the play. So, sound in the theater is exactly the same. Everything you hear during the performance, the actors' voices, the pre-show music, the underscoring themes, rumblings from everything just outside the door, distant thunder, telephone rings, doorbell chimes, they're all designed with one purpose in mind: to immerse the audience in the world of the play. So now we're starting to get into sort of the who and sort of how we accomplish that. The sound designer is essentially the same as every other field. They have the responsibility of sort of interpreting the play, the script, and all the little nuances that sort of come with it. He or she basically provides the designs for all the pre-recorded music, the sound effects, and any sort of reinforcement of sort of the live voices, musical instruments, and the sound elements. The designer is responsible for all sound-related technical drawings and sort of the specifications for any sound equipment that should be rented, leased, purchased, or have on hand. They're also sort of responsible for sort of setting all of those sound cues, such as levels, where they're going to come from, and how it's going to go. At the highest level of professional theater, sound designers tend to specialize in either musicals or sort of non-musical plays. Given that not every producing organization can hire separate sound designers for musicals and non-musical productions, many sound designers do have a little bit of cross-training, so they can sort of compete in all sort of three primary areas. And those three are sound scoring, sound reinforcement, and sound system design/operation. Once they've sort of done their job, it is then sort of put upon the soundboard operator, also known as sort of the A1. And they're basically responsible for running the show as intended by the designer, such as cues that have been pre-recorded and timing them just right in all of the sequences of the performance. Any production that maybe requires additional sound reinforcement will frequently have an assistant production sound engineer, or also known as the A2, or the wireless mic technician. While their main responsibility is to ensure that anyone who is wearing a microphone has enough battery life, needs to switch it out, or any kind of transfers or handoffs, this technician is responsible for ensuring that everything gets to where it's supposed to in an orderly fashion. In larger musicals, there may be an additional sound technician known as the A3. One of them might be sort of submixing the orchestra, while the other A2 is the one working with the wireless mics themselves. It really just depends on what production is going on as to what specific duties or assignments the A2 or A3 will have. You then have what is known as sort of the head sound engineer, or also known as the sound system engineer. They supervise the sound crews who basically install the sound system. They also ensure that the system functions properly and as designed. There are a lot of times in which a performance or a show may require some additional speakers to be placed throughout the auditorium, or something specific may need to be added, such as sort of placements for some of those practical effects, such as sort of a phone or a doorbell ring. It is the responsibility of the sound engineer to sort of ensure that all of those things get placed and put where they're supposed to and work as intended. So if a sound design creates sort of the oral environment for the play, we have to sort of ask the questions, sort of how does it do that? What does it consist of? And how is it made? A sound design is composed of one or both of sort of these two elements, sort of the sound score and sound reinforcement. The sound score is the music and sounds used in support of the production. The music, whether pre-recorded or written specifically for the production, includes sort of the intermission, pre- and post-show music, and sort of any music used in sort of the underscore moments or sort of sub-scenes within the play. Irrespective of the sort of elements chosen to sort of create the sound score, the audience's main focus should almost always be the actors' voices. A play or musical is doomed if the audience can't hear or understand the dialogue or the lyrics. Because many sound designers sort of come to the theater with a background in music, it is not also surprising that they frequently sort of compose some original music used in sort of this sound score. In fact, many of them think of the entire sound score. So they think about the music, the sounds, and all the effects as sort of a musical composition, because the musical elements of pitch, rhythm, tempo, and loudness are at sort of the core of both creating and editing music and sound. Sound reinforcement, on the other hand, is just sort of the use of a sound system to amplify and process the voices of the actors, singers, orchestra, or the sound effects. A good sound system should do this pretty much as transparently as possible. After sort of the first few moments of the performance, the audience should almost be completely unaware that a sound system is even being used. Sound reinforcement is typically used to sort of balance sort of the loudness of the vocals, orchestra, and sound score, so that the actors should almost always be heard above everything else. This basically means that they try to get like a perfect blend of everything and create sort of the mix of the performance. Without reinforcement of vocals, an orchestra sound will almost always sort of take over a singer's voice. Creating sort of this perfect balance between those two can create sort of that perfect harmonious sound to make it sort of seamless between the two. And it's also sort of this sound reinforcement of creating the perfect level for, in the cases of musicals, that if someone is talking or speaking, that their voice is amplified enough and then can seamlessly sort of go into a musical number with sort of the subtle changes in sort of the amplification of someone's voice to where you don't even notice it. To develop sort of a working knowledge of sort of how sound operates, you'll first have to sort of understand sort of the nature of sound. Sound is a pressure wave that moves in the air and at sea level at about 1,130 feet per second. The pressure wave is instigated by a source such as a drum. The drum sort of compresses the air immediately adjacent to the drum head when the head is struck with the drumstick. This compression wave travels sort of through the air until it sort of strikes a receptor, in this case, the human ear. The ear then converts sort of that mechanical force of the pressure wave into a sort of neurological impulse that is sent to the brain, where the stimulus is then interpreted as a drum beat of a particular tone and or quality. So one of the ways that these waves are sort of represented is sort of by the frequency. Frequency is sort of the rate or measured in sort of cycles per seconds, hertz, at which an object vibrates. At one time or another, sort of most of us have sort of strung a rubber band between our fingers and then sort of strummed it. The rubber band vibrated and made a specific sound. We then noticed that if we were to stretch the rubber band sort of tighter, the sort of number of oscillations or vibrations made by that same rubber band increased and the pitch of the sound got higher. This sort of demonstrates sort of the direct relationship that exists between frequency and pitch. As the frequency increases, the pitch also increases. Most humans hear frequencies sort of ranging between 20 and 20,000 hertz. While it should be noted that sort of most people can't hear a lot of sort of the highest frequencies, and while they often sort of experience some of those lower frequencies as more of a sort of physical vibration than a sound. If anyone sort of has ever experienced a sort of subwoofer from a car, you kind of feel that vibration every time something travels through it and basically creates sort of that shock wave that you feel against your body. There is sort of a rough correlation sort of between these two terms, intensity and loudness, however, but there are sort of technical differences between the two. Intensity refers to a measurable quality of the power of sound, normally expressed in decibels. Loudness is basically just a subjective term that sort of describes a person's personal perception of sort of the sound intensity. The decibel, or abbreviated dB, is just the unit of measurement of sound intensity. Decibels are used to measure both sort of the intensity of sound waves in the air, decibel SPL, or decibels, where SPL basically stands for sort of the sound pressure level, and the electronic signals that represent sound waves, such as decibels M, where it's milliwatts, or dB, capital W, watts, for electrical intensity. Now, while we sort of look at these sort of sound waves, we start to get into sort of the study of acoustics, where it's sort of the study of the generation, transmission, and reception of sound. In theater, acoustics is concerned sort of with the study of the qualities of the stage and auditorium spaces that affect how an audience actually hears and understands everything. A theater with good acoustics will allow sort of every member of the audience to hear, understand everything that's being said by actors sort of being anywhere on stage. An almost limitless number of factors, however, sort of determine the acoustics of any given auditorium. The room's physical shape vitally affects sort of the reflection of sound. If the walls are parallel, the sound will sort of bounce back and forth between them, sort of reducing the intelligibility of every sort of word spoken. To reduce a lot of this sort of reflection, many architects slightly will curve those walls of the auditorium so that it is less likely and less frequent that those sounds will reflect or bounce off, making it fairly unintelligible. The materials can also sort of greatly affect how everything is also perceived. The walls, ceiling, and floor have sort of the greatest impact on sort of those reflection of sound. Obviously, hard surface materials such as wood, metal, plaster, and everything similar reflect sound quite easily, whereas soft or open surface materials such as cloth, foam, or loosely spun insulation will absorb a lot more of that sound. So now we get into sort of what is known as timbre. Timbre basically refers to the distinctive quality of any given sound. That is sort of what makes one sound different from another, or to sort of better put it, how a trumpet sounds different than a violin. These differences are based on sort of the harmonics made by that sort of sound producing body. Pure sounds, such as shown here, hardly ever sort of occur in nature. Most sort of natural sounds, such as voices, violins, or anything else, produce sort of a variety of overtones or harmonics, such as seen here. These frequencies are based on sort of the pitch, these frequencies based on the pitch are fundamental or base frequency. The amplitude or sort of loudness of each harmonic will be less than the loudness of the fundamental frequency. And the amount of each harmonic in the final tone will be determined by the physical structure of the source. Now, while a lot of this is a lot of the technical babble, it is important to understand. We then sort of get into what is known as phase. Sound waves are basically caused by the cyclical compression and decompression of molecules through which sound is traveling. In air, from the moment a sound is instigated, the air pressure increases as the air molecules press against adjacent molecules until the sound reaches its sort of loudest moment, a sort of pressure peak. Then decreases until it reaches the maximum level of decompression, at which the point of compression cycle starts all over again. It's important to know a signal's phase, whether that signal is electronic, analog of a sound wave, or an actual sound wave itself. The reason is because the intensity of the sound will be affected if the signals are sort of out of phase. If one starts at sort of the exact same time as sort of shown here, what actually happens is you sort of get what is known as sort of phase cancellation. And this is actually some technique that sound engineers may try to do if they're trying to sort of get rid of a specific frequency out of maybe a soundtrack or anything like that. It is possible to sort of use this sort of signal canceling to sort of get rid of or remove vocals from a track. So if you would almost think about doing karaoke, basically what that is the vocals have basically just been completely removed from those tracks in order to just give you the music that has been provided. So while it's important to understand sort of the acoustics, this then sort of brings us into sort of the sound production. Being able to sort of perfectly balance any sort of auditorium is practically impossible, especially if there is both sort of speeches, lectures, and music. The reason for this is the two ranges vastly affect sort of how a structure should be built. Now, there are instances where one may be more prominent than the other, but that doesn't necessarily mean that you can't do or perform music in sort of a lecture hall. It just will affect sort of the overall production level unless you sort of create something. And that sort of leads us into sort of the sound system configuration. So in this image here, you sort of have sort of three different examples of how this can be done. You have sound reinforcement, sound recording, and sound playback. Now, the equipment configuration for a single sound reinforcement system, as shown there at the very top, is basically just a microphone, which is sort of a type of transducer. It picks up the sound. The microphone will then convert that sound into a weak electrical signal. That signal is then sent into a preamplifier in the mixer, and this preamp basically boosts that electrical power of the signal into sort of the signal processing of the mixer. After the sound has been processed, it is then sent back out of the mixer and is sent into a power amplifier. The power amp substantially boosts the overall power of that signal and then sends it to a loudspeaker, where it is then sort of transferred back into a sound wave. The second version, the sort of sound recording, alters sort of how that path is transmitted. Basically, what I'm doing here, doing these recordings, is one of these sort of examples where I'm using the internal microphone of my computer to pick up the sounds, and the mixer is basically the computer processing ability, and then that is transferred into a computer program where it can be manipulated in any way, shape, or form. The sound playback is how you would sort of describe if you were to plug your phone into your car system. You basically have the computer being your phone or a CD or a cassette, and it then goes into the system or the mixer and then is sent into sort of your internal amplifier, which then is transferred into all of your speakers. So obviously, depending on how your system is set up, if it is custom, if it is stock, you can get a wide range of effects through that system. So basically, every sound system works on sort of that principle that we just talked about. Here, we're going to start discussing sort of the differences in microphones. There are three basic types of microphones used in sort of theatrical sound design. The ribbon microphone. Ribbon microphones use an extremely thin strip of corrugated metal sort of suspended between these two poles of a magnet. And the air pressure of the sound waves moves the metal sort of back and forth to sort of generate an induced voltage between the two ends of the ribbon. That voltage mimics the frequency and intensity of the sound source. The ribbon microphone has an excellent sort of frequency response, but is really delicate. Typically, just sort of blowing into the microphone can easily break this type of microphone. High-quality ribbon mics are frequently used in sort of recording studios and sometimes for pit orchestras. But their delicacy usually makes them a little too fragile to sort of stand up to the everyday abuses they would receive on stage. The dynamic microphone is where the heart of this microphone sort of comes from is a magnet surrounded by sort of a wire coil. One end of the coil is sort of firmly attached to the diaphragm of the microphone, and when sound waves strike that diaphragm, both the diaphragm and the coil sort of start to move back and forth. thus generating the induced current that mimics the frequency and intensity of that particular source. Dynamic microphones have a very good frequency response. They are fairly rugged and are pretty suitable for sort of on-stage use and even in recording studios. And last, we have sort of the condenser microphone. The condenser microphone is sort of the most complex that is used in theater sound. The diaphragm, which is made up of thin conductive material, forms one plate of a condenser or capacitor. The constant voltage is applied across these plates, as you can see here. When a sound wave strikes the diaphragm, the pressure changes sort of that spatial relationship between those two plates. This causes that change in the condenser, which changes the voltage applied across those two plates. That voltage variation mimics that pattern again of the sound waves generated from the source. The condenser microphone has really good frequency response and dynamic range, where the dynamic range is basically the sensitivity to changes in loudness, sort of the ratio between the largest and smallest intensity levels of sound. Condenser mics, however, sort of require what is known or require a sort of power supply. And this power supply is basically known as sort of phantom power. And that power is basically generated from the mixing board itself. Most boards will either have it automatically turned on, or in most cases, there is usually a small switch that can generate this sort of phantom power for this particular type of microphone. Now, while there are just these sort of three types of microphones, we do have to sort of discuss a little bit about sort of the microphone pickup pattern. And as you can sort of see here, they may look like just sort of really random sort of shapes, but they sort of all serve a different purpose. More commonly seen are your sort of omnidirectional or cardioid microphones pickup patterns, simply because a lot of times you may not have a microphone placed on an actor and you need to be able to pick up sound from any kind of direction. Thus, you would want to use sort of that omnidirectional, which can pick up everything in its surrounding area. The cardioid, however, is the most sort of commonly used and seen by anyone who's wearing a microphone. If you've seen in just about any kind of interview or any kind of news reporters, they'll typically have like a little lapel clipped with a microphone on them. The cardioid basically picks up from one strong or gentle direction. Thus, it'll have one side which has sort of the microphone face, and then on the back side it won't have anything. So you would generally want to have that flattened side against the individual, and thus any sort of sound that is produced by them will be picked up using that particular pattern. While these other ones are fairly important, just to sort of depending on what you're doing, we won't go in depth to each of those. While it's not a sort of specific type of microphone, we do also have to discuss sort of wireless microphones. And what wireless microphones do is they use a low wattage FM radio transmitter to sort of broadcast that particular microphone's signal to a receiver. And that then feeds that signal to the mixer. And with sort of these wireless microphones, you sort of again can create more commonly seen as the handheld that any kind of performer might use in a music video or anything like that, or down to the sort of smaller ones like I just discussed, where a news reporter or an actor may have one clipped to them to then have that signal then transferred to the receiver. The great thing about these wireless microphones is they're obviously ideal for musical numbers and a lot of things where the actor sort of has a lot of movement in their blocking. The reason for this is if we had wired mics connected to all of them, it would pose a really bad tripping hazard for everything and around. Moving on to mixers then, they basically serve sort of two main purposes in a sound system, either to signal routing and processing. The process is sort of best described sort of by this example that we have here. It basically shows sort of a mixer's input and then output channels for sort of a hypothetical. In this example, we have a wireless microphone and a playback computer being plugged into the inputs of the mixer. As far as the outputs go, we then have a wide range of sort of possible locations for sort of the output signal to be sent. So it can be sent to any one of those particular speakers, depending on sort of where they're located. One other way to sort of look at this is, by example, the soundboard operator could potentially route the individual's microphone to sort of the closest proximity to where they are on stage. So if they were somewhere to the left, you could basically pan or funnel most of that sound or signal to everything that is on the left side, or all of those speakers located near that position. And you could sort of follow the actor around the stage by sort of moving where you're sending that signal. While that is usually not the case, it does sort of highlight the sort of capabilities of sort of manipulating the signal and being able to focus it in a particular area. This is sort of ideal for a lot of sound designers to sort of create realistic effects coming from a particular source. Ideally, you could potentially do this for like a phone ringing on stage or somewhere off stage. If you had a speaker located in that general area, whenever you play that particular sound cue, the sound would obviously then be played only through that particular speaker. And that can give you a lot more of a realistic feeling when it comes to where you are. Now, there are, it really depends on sort of the brand, make, and model again, but most mixers have about 8 or significantly more input channels. So it has the ability to sort of house multiple microphones and or other input devices, such as any of these here. And then the outputs, again, sort of vary depending on what type of board that you have, such as this one here. But you have sort of a lot of range and potential generally when it comes to where you want to do. There are typically 2 types of audio mixers, and those are either analog or digital. And I mean, really, a technical discussion of sort of both of these is beyond sort of the scope, this sort of introductory class. But a brief sort of synopsis of the 2 is analog, obviously sort of precedes all digital forms, and each channel had sort of its own control and function, which meant you had the ability to change everything manually in order to sort of fine-tune what you wanted the final signal to be produced. Digital boards, on the other hand, have a lot of internal processes that allow you to do a lot of this sort of internally, and have it sort of saved or pre-programmed depending on sort of what you're working on. They also, the digital versions, have the sort of capability of sort of recording an entire show, if you so had sort of the time and investment to sort of do that, which sort of means that you can sort of preload cues and then hit basically a same go button. And what would happen is a preset level would be sent to the board, and then it would automatically adjust every single one of those sliders to that pre-recorded setting, allowing you sort of a lot more freedom to sort of fine-tune if need be, or to sort of have a lot of hands-free action to where you can focus on just running the show. Some of the things that we can sort of discuss about these two is sort of that all mixers will sort of typically contain equalizers to sort of shape the frequency response of the signal by either boosting or attenuating relatively narrow frequency ranges of that initial input signal. In addition to sort of that equalization, each channel of a digital mixer is normally equipped with a compressor, a gate, and sort of a signal delay. All of these sort of devices allow you to sort of further shape the sound wave itself. The compressor is basically an electric device or software that automatically reduces signal amplitude when a predetermined intensity level is reached. So basically that would allow you to sort of create a maximum threshold for the sound to be limited to. A gate is basically a device or software, again, that will automatically increase the gain, gain being sort of the an additional volume thread, the gain of an input signal, basically effectively turning it on or off when a predetermined intensity level is again reached. The signal delay, however, is sort of exactly like it sounds. It allows you to sort of program or specify an amount of time before that signal is actually sent off to the next device in the system. While not directly associated with most mixers, one of the great things that can happen is what is known as sort of the active crossovers. And this is, again, just sort of another signal processing capability where signal is split up into sort of two frequency components suitable for a specific loudspeaker to reproduce. For example, a two-way active crossover might split a signal at 1200 hertz and then send those frequencies below 1200 to an amplifier powering a woofer, and then the signals that are above 1200 hertz to an amplifier powering a high-frequency horn driver. Now, we'll cover the speakers here in a little bit, but that basically allows you to send the signal to an appropriate speaker, which is better created to process that particular signal. The active crossovers digital delays are used to help sort of compensate for the differences in sort of arrival time to the listener. Again, that sort of allows you to change how long it takes for that signal to be processed and then sent out. And then we have the power amplifier. Now, while there's a lot of sort of processing in sort of any standard sound system, the power amplifier basically just takes that sort of low voltage signal and then boosts it up to a higher voltage signal capable of sort of driving or sending that signal through the loudspeakers. Power rating of any amplifier is pretty much the most important stat to know, depending on what kind of system you are running. If you were to try to sort of underpower a particular speaker with a sort of lower end amplifier, what will tend to happen is that signal won't be able to be boosted enough, and it'll probably start to sound a little garbled or distorted in such a way. Or sort of vice versa, where if you have too strong of an amplifier and you don't have a loudspeaker sort of capable of taking that particular signal to that level, you can often damage the speakers themselves. So as mentioned before, the loudspeaker converts the electrical signal from the power amp back into sound waves. The signal activates an electromagnet attached to the loudspeaker frame. This electromagnet generates a field that corresponds in intensity to the frequency and loudness of the electrical signal emitted by the amplifier. The variation in this magnetic field causes a voice coil, usually attached to the rear of a flexible cone, to move the cone forward and backward in a pattern that mimics the frequency and loudness dictated by that signal. Speakers work most effectively and efficiently when they are designed for a relatively narrow frequency range. Speakers are generally classified as low frequency, or woofers, mid frequency, mid-range, and high frequency, tweeters. Almost all woofers are cone-type loudspeakers. Mid-range speakers and tweeters are also made with cones, but loudspeakers for live performances are typically manufactured using pressure drivers and horns due to the high sound pressure levels and carefully controlled coverage angles required. As mentioned before, the importance of sort of having a sort of narrow frequency range, providing sort of the best sound that you can get, really comes true with these types of speakers. The subwoofers or woofers generally want to run some of the lowest frequencies imaginable, and that's where you can kind of get that sort of physical reaction or physical wave or force being emitted from the woofers. One of the best examples of this is back in college during a performance of Into the Woods. Our director wanted a giant's footsteps to basically reverberate throughout the entire audience. And as sound designer for that show, I had to come up with the various ways and positioning of all of our speakers to help showcase this. Well, a friend of mine was able to get in touch with someone, and we were able to get two large subwoofers, and by placing them close in proximity to sort of corners of the building, whenever we would use or send a signal to those speakers, the entire building, which also housed a couple offices and other departments, caused basically everything to shake. And we actually got complaints after one weekend of test running these that some of the items in or on their desks or shelves were displaced or fallen over due to how much we were running them and how effective that frequency range was actually being emitted. So some of the other types of speakers that we sort of can come across are known as bi- and tri-amplified speakers. The bi-amplified speaker systems basically use an active crossover to sort of split that signal from the mixer into the low and high frequency ranges. This separated signal are then sent to the two amplifiers. one of which powers a woofer, and the other a high frequency speaker or driver. The tri-amplified systems use that same principle, except they sort of split it into the low, mid, and then high frequencies before sending that signal out. Another system that we can come across is known as the passive crossover. The passive crossover split the signal after the power amplifier. They don't have any kind of processing capabilities other than sort of that split in the signal into sort of those 2 or 3 frequency ranges for use by the individual speakers in the system. Speaker cabinets basically are mostly low frequency speaker cabinets designed to sort of enhance that reproduction of those low frequency sounds, as I sort of just discussed, because those low frequency sounds require a lot more power to produce than mid or high frequency. When the cone of a woofer sort of moves forward, it starts to compress air, which then produces sort of the sound waves as shown here. When the cones move backwards, that same amount of air is compressed and produces that same amount of sound wave as it was received. If the speakers were sort of mounted in a hole in the wall, sort of between those 2 rooms, as I mentioned with my example, it would produce that sort of same frequency, quality, and intensity of sound in both of those rooms. So now we sort of move into sort of how or the loudspeaker hookup methods. This sort of needs to begin with another sort of caveat. If you don't know what you're doing, don't do it. It is very easy to sort of damage either the power amplifier or the loudspeakers if speakers are hooked up incorrectly. It's always important to sort of understand what the manufacturer's recommended practices were before sort of connecting any type of speaker to the power amps, and definitely before turning anything on. We'll sort of quickly go through this as it's a lot of the more boring stuff, but to ensure the best quality sound from the system and of the speakers or the speaker system impedance, normally 4, 8, or 16 ohms, must watch the output impedance of that amplifier. In other words, when you connect a speaker system of specific impedance to power amps output with that same number, as sort of shown here. Sometimes it's desirable or necessary to sort of drive more than one speaker with a single amplifier. This can be accomplished by wiring the speakers in either parallel, as seen with that image. Power amplifiers, though, should be connected to the speakers with professional grade audio hookup cable. The reason for this is that signal loss can occur when the resistance in these cables are too high. To avoid this, there's a few little rules of thumb that we can sort of follow. The cable run between the power amp or wall-mounted speaker outlet and the speaker is less than 50 feet. Make the connection with 14 gauge audio hookup cables. Runs between 50 and 150 feet require 12 gauge cable. And then all speakers or power amp cable connections should be made with a specific type of connector.